Okay guys, today we are on page 29 in your notes packet, and we're going to take a look at another type of transformation. You'll notice the top of your notes today says non-rigid transformations. That's because what we're going to see today means that the shape of our graph can change a little bit. So our absolute value graphs are still going to look like V's, our quadratic graphs will still look like U's, our linear graphs will still look like lines, but we can distort their shape a little bit. We can stretch them out or flip them, and so that's what we're going to look at for today. If you remember in your activity from the other day, the last slider that you could change was for an a value, and if you looked at your function it said a times f of x. We see some different things happen with a depending on its specific value. So that's why we're talking about a all by itself. The first thing I want you to remember from your activity the other day is that if a is positive, your graph maintains its original orientation. So let's use absolute value graph for our example as we talk about this. So if a is positive, our graph's going to maintain its original orientation. If a is negative, then our graph is going to flip. Doesn't matter what negative value it is, if you have a negative in front of your function, any negative value at all, our graph is going to be upside down. It's going to be flipped upside down. The other things we need to consider for a are the actual values for a. So if a is a number greater than 1, then our graph is going to stretch or narrow. Sometimes we'll see it called narrows. If a is a number less than 1, but bigger than 0, so not negative, but a fraction or a decimal, we'll say that's less than 1, our graph widens. Okay, so one thing I want to point out, fraction does not necessarily mean widen. The number 4/3 is a fraction, but it would actually stretch my graph because this is a number greater than 1. So just something to keep in mind as we're working for today. So let's take a look at our first example. Just like we did in our previous notes, we're going to identify the parent function, describe the transformation, and then graph our new function. So here I have 1/2 times the absolute value of x. So that means that my parent function would be the absolute value of x, right? That same graph, but without any of the bells and whistles. And so in a lighter color, just like I did for a couple of our problems yesterday, I'm going to just sort of sketch that absolute value graph. So we know the graph that we're starting with as we work to transform it. My a value here is the only change. It's a positive number less than 1. So my absolute value graph is going to maintain the same orientation, but it's going to widen by a factor of 1/2. What that means is that our sort of center point here, our corner of our V, will stay in the same place, but instead of the next point on the right being up 1 and out 1, it will be up 1/2 and out 1. Okay, so all of these are going to be sort of shrunk by 1/2. So instead of this point being up at 2, it will just be at 1. I'm cutting that distance in half. I'm cutting its vertical distance in half. So there's my graph for this new function. Okay. Again, I cut that vertical distance in half for each of my points. Now let's take a look at our second example here. We have -2 times the square root of x. Our parent function here would be the square root of x. Right? If I take away the extras, I'm just left with the square root of x, so that's my parent graph. And I'm going to put that parent graph on my coordinate plane over here. Again, in a lighter color, just so I have it for reference. Okay. So there's my parent graph. And then I want to graph this function. So the negative is going to flip my graph, so I'm not going to keep the same orientation. It's going to be flipped this way. Okay, I flip over that x-axis, flip horizontally. And then since it's a 2, that's going to stretch my graph by a factor of 2. Since I haven't moved left, right, up, or down, my sort of end point will stay in the same spot. It's these points, all the other ones, that are going to change. So the first thing I'm going to do is flip. So instead of this point being above the x-axis here at 1, 1, I'm going to flip it down. And then I'm going to stretch. So that means I'm stretching that vertical distance. Instead of being 1 away from the x-axis, now that point's going to be 2 away. And I'll do the same thing with my next point. Okay, this guy right here is going to flip down, and then I want to double this distance. I'm stretching by a factor of 2. That means I'm going to double the distance. So instead of being 2 away from the x-axis, now it's going to be 4 away. So that's my transformed graph. We're going to take a look at some more examples. Turn the page for me. On page 30, we're going to sort of take this in reverse. So on page 30, we're starting with those parent and child graphs. Remember, the black is our parent graph. Or the solid, I should say, is our parent graph. The dashed is our child graph. So I want to describe the transformation and then write that new equation. So from my parent graph to my child graph, the first thing I notice is that my child graph is flipped. Right? The child graph is upside down. And then if I look at the points here, let me scoot this over. If I look at the points that I have here, our absolute value graph, we know that the first point to the right should be up 1 and out 1. This point here is down because we're flipped, and we go out 1, but only half of the way there. My second point out should be up 2 from the x-axis. This is down since we're flipped, but only 1. So I've compressed or flattened this graph, okay? Widened this graph, I guess I could say. Widened, or we'll also see the word compressed. By half. I've cut that vertical distance I used to travel in half. So that means my a value has to be negative, and it has to be a half. So my function here will be negative 1/2 absolute value of x. Let's take a look at another example. Again, we're going to describe the transformations that we're going to see here and write the function for the child graph. So again, the solid is our parent. The dashed is our child graph. Okay. This is an x squared graph because I have that U shape. And then notice to get from that center point, this is called the vertex. We'll talk more about that later on in Algebra 1. But to get from this center point to the next point, I'm up 1 and out 1. On this graph, my center point is moved, so I've gone to the right 1. And then I've also gone 1, 2, 3 up. And then to get from my center point to the next nice point, instead of going up 1 and out 1, I went up 2 and out 1. So I've stretched this graph by a factor of 2. Okay, we've doubled that distance, that vertical distance to get to the next point. It used to be 1 up, now it's 2 up. So I've stretched this graph. So I'm going to write my function here. I know this is an x squared function. Right 1 and up 3 stretched by 2. Stretched by 2 means I'll have a 2 in front for my a value. To move to the right 1, these were the transformations we talked about last time. So this would be x minus 1, with the square outside of the parentheses. And then to go up by 3, we add 3 at the end. So there's our function to describe that dashed child graph. We're going to take a look at just a couple more examples together for today. So go ahead and turn the page to page 31 for me, please. And we're going to look at a few more. So at the top of page 31, we're just going to describe the transformations that we'll see based on the information that we have. So we're going to let f of x be our x squared graph. Since we're not graphing anything, that doesn't matter so much. But what we do want to do is describe each of the transformations that we'll see here. So for a, 2 times my function means that we are going to stretch our function. We're going to double those distances. Okay, so this is just a stretch by 2. Stretch by 2, by a factor of 2. For b, negative 2 f of x, we're again going to stretch by 2, but that negative is going to flip our graph. So I'll have an upside down, really skinny parabola. So we'll flip and stretch by 2. For c, 3 f of x is going to stretch our graph again. Now remember, for our parent graph, we said that point is normally up 1 and out 1. When we stretch by 2, we double the distance, so that point's up here now. If I'm going to stretch by 3, that means I'm going to go up 3 and out 1. So this will stretch by 3. For d, we've got 3 f of x plus 4. So again, we're going to stretch by 3. But then we're also going to move everything up 4. So I'll shift everything up 4, and then my graph will be stretched out. E, 1/2 f of x. This is going to be a compress or a widen. So instead of going up 1, out 1, we would go up half, out 1. We're going to have that distance, that vertical distance. So widen or compress, you'll see that term again, by a half, by a factor of a half. And then f, negative 2 times f of x minus 1. Well, we know what the negative 2 in front does. It's going to do the same thing that it did in b. So we're going to flip this graph. We're going to stretch it by a factor of 2. And then that x minus 1, remember we wrote that as part of our function back on page 30 because we wanted our graph to go to the right one. So that's what this graph is going to do as well. It's going to shift to the right 1 place. For the last couple examples we're going to look at, we're actually going to go ahead and draw those transformations. So here's our graph that we're starting with. This is our parent graph. And on each of these others, we've got a description of a transformation, and we're going to actually draw that transformation. So here's our parent graph. This is saying to get our child graph, take 2 times the parent graph. So that's going to be a stretch by 2. So that means that every vertical distance we see, we're going to double. Okay? So I can keep my points on the x-axis here, but the vertical distance that I have is going to double. So instead of having a y-intercept at 2, my y-intercept is going to be up at 4. This corner point as well, that vertical distance is going to double. So instead of being at 2, 2, it's going to be at 2, 4. And then the same for the point on the other side. So this would be my transformed graph. I've stretched it. I've doubled that vertical distance. For C, this is saying to get my child graph, take 1/2 your parent graph. So this will be a compress or a widen by 1/2. that means we're going to take that vertical distance and cut it in half. So let me scoot this a little bit so we can still see our original. So my x-intercepts can stay the same. My y-intercept is going to be cut in half. So instead of my y-intercept being at 2, it's going to be at 1. Okay. And then the same for these points here. Instead of 2, 2, I'll have 2, 1 and negative 2, 1. So I've compressed it. That vertical distance is what's changing here. And then finally, for my last graph, this is saying to get my child graph, I'm going to take my parent graph and multiply it by negative 3. So the negative's going to flip. We're going to be upside down. And the 3 is going to stretch us out. Instead of stretching up, we're going to stretch it down because we're upside down. So again, my x-intercepts can stay in the same place. Instead of going up 2, I'm going to multiply that distance by 3. So here we multiplied by 2 because we were stretching by 2. Here we're going to stretch by 3. So instead of 2, it will be 2 times 3. So I'm going to go down to 6. Remember, we flipped with that negative, so we're going down. So 1, 2, 3, 4, 5, 6 would be right there. And then this point here is going to flip down, so it would be there. But then we're going to multiply it by 3. So again, instead of a distance of 2, we've got to multiply that by 3. So this distance would be 6 as well. And the same thing on this side. I had a point here. Flip it over the x-axis, that puts it here, and then triple it. Since we're multiplying by 3, that puts it right there. So that's our new transformed graph. That's it for our notes for today. You have a homework assignment on Delta Math. That's going to be sort of all the transformations we've talked about kind of mixed together. If you have questions, make sure that you ask, and we will do a little bit more practice on this tomorrow as well.